In the previous lecture, we talked about electricity in terms of electric current. We're going to introduce another physical quantity or concept of electric potential difference. This is another way to kind of define electricity as well. And what potential difference really means is it's the amount of energy we have per unit of charge. But we'll get into that further in the lecture. So suppose that an electric stove element is connected to a battery and the element begins to heat up. If an ammeter is connected to the circuit, it will measure a fairly large current because we need a lot of current in order to produce that thermal energy. You might say the element is using electricity, but what does this mean? What is the element taking from the current? So how is it using electricity? As current passes through the stove element, it experiences an opposition to the flow. So there's something that's kind of opposing that current flow. It's trying to slow the current flow down. That the current flow still kind of powers through it though, and by doing that, it loses energy, and that energy that it loses is that potential, the electric potential energy that the electricity had. So there's a difference in the electric potential after passing through the element. That difference, we give it a symbol of V. So the electric potential difference it's measured between kind of 2 points in a circuit, like across a load. In this case, we're talking about the stove element. So across that stove element, there's an electric potential difference. There's a difference in the electric potential energy before and after. We measure this in a unit called volts, and electric potential difference is sometimes called voltage. So it is the difference in electric potential between 2 points in a circuit. The SI unit is volts, capital V. The symbol is a capital V, and we sometimes also call it voltage. And really what we're doing is we're giving off, there's a certain amount of energy we have per unit of charge that moves through that. So voltage could also be considered as energy per unit charge. So that lost energy, that lost electrical energy, it transmutes into thermal energy, and I guess light energy in this case because the element is visibly heated up. So that is how that energy that's lost electrically is transmuted into other types of energy across the load. We can measure the electric potential difference across something using what's called a voltmeter. Now, this is opposite to how we would connect the ammeter. We would have to connect a voltmeter across something or through what's called a parallel connection. So here we see this light bulb, and our voltmeter has to be connected across the light bulb. In this case, we'll see what the difference, the potential electrical difference is between this point and that point, and that difference is equivalent to what we sometimes call the voltage drop across this light bulb. So a voltmeter, the symbol for it is a V with a circle around it when we're drawing a circuit diagram. It's connected in parallel or across a load, and it is used to measure the potential difference between 2 points in a circuit. In an ideal circuit, the connecting wires and the control device do not affect the amount of electric potential and therefore do not cause a voltage drop. However, in a real circuit, the connecting wires and control devices can cause a voltage drop. So basically what this slide is saying that the voltmeter shouldn't affect electricity in the circuit, but sometimes it will. Just an ammeter should have a resistance of 0, and a voltmeter should have a high resistance, because the idea behind a voltmeter is we don't want to have too much electricity flow through it, because if that happens, then we're taking the electric current flow through the load away. So that's the situation. Here's a student who connected their voltmeter incorrectly. They're trying to connect it in series. Because the voltmeter has a very high resistance, we probably wouldn't even have electric flow in this case, unless we have a very high battery, a very high voltage battery. We won't have any electric flow. So identify what is wrong in each of the following statements. It says a voltmeter must always be connected in series. Well, a voltmeter has to be connected in parallel. The other statement is, sorry, I guess there's another thing here. It says an ammeter must always be connected in series. So if we want to correct that, the ammeter is connected in series, the voltmeter is connected in parallel. This statement says a series circuit has more than one complete path. I guess by definition, a series circuit has only one complete path. It's really just a circuit or a loop. A parallel circuit has more than one path. Connecting a voltmeter in series will allow only a small amount of electrical energy to travel through it. Well, if we connect the voltmeter in series, we'll kind of prevent the circuit from even flowing because of the high resistance. It probably will prevent the circuit from even flowing. So connecting a voltmeter in parallel prevents a lot of electrical energy going through it, so that it's only measuring a voltage drop rather than actually contributing to the complexity of the circuit. This statement says a parallel circuit can only have two complete paths. A parallel circuit has more than one path. So we can have a parallel circuit with 3, 4, 5, 6, 7, 8 paths or more. Another statement here, I think this is the last one. It says a complete circuit contains a source of electrical energy and a load. This one I kind of disagree with, because it says a switch. It says a complete circuit contains a source of electrical energy, a load, connecting wires, and a switch. We don't necessarily need a switch for a complete circuit. An important part of the body's nervous system is the neuron. So neurons are nerve cells that receive, interpret, and transmit electrical messages. So you might not know, but your brain actually transmits information using electricity. And those neuron cells kind of act as little batteries. They actually have a voltage of about 60 to 90 millivolts. In order for your brain to send information to your body through the nervous system, or your nervous system to send information to your brain, these little neuron batteries in your nervous system and your brain end up sort of sending an electrical signal back or forth, and that tells your body information that you can then act on.